So we have this piece of axle with 3 different cross-section diameters, 8 millimeters, 15 millimeters, and 6 millimeters. We have multiple external torques applied there, and we're asked to determine the highest shear stress in twist. Well, in this example, it's best to start with making a free body diagram. So we start from free body diagram, FBD. And we draw it in here. So let's start from the first cross section here, like that. Like so. And now we have here external torques. From statics, you should know that defining the direction into which these arrows are pointing in free body diagram for torque, you can use the right hand rule. So with your right hand rule, we can see that the first torque is pointing to the direction of the fingers, which means that the external torque is gonna be pointing this direction. You also remember that marking the torque in the free body diagram is done by using this double arrow, so 10 Newton meters in here. Then I will mark here the cross section so it's better to easier to visualize, like so. In here we have torque to the opposite direction, 70 Newton meters, like that. And in here we have torque once again to the left. This one is 80. And then finally at the end here we have torque which is pointing this direction, and the value for this one is 20 Newton meters, like so. So next thing that we need to do in this example is to define the internal torque in the material. So you might remember that we've previously done this same kind of thing for normal stress. So what we do is that we draw the internal torque diagram for this case. So I draw it here underneath the free body diagram, so it's better to understand. And now you might remember from statics that how you can define which direction of internal stress is positive. Well, we have defined that the positive torques are pointing to right, positive forces are pointing right and up. So in this case, when the external load is to left, it means that the internal load at this first section from starting from here must be to the right. So here the internal torque value, it jumps to 10 and it points to it's on positive side, so we're at value 10 of internal torque here, 10 positive, like so. Then we come here to the second diameter where the torque value is 70 newtons and it's pointing to the opposite direction, which means that we're going to go up here and we're going to go all the way up to 60. So we go to the negative side and we go to value of 60. So this one is 60. We stay on that value until in here we come again to next torque, which is 80 Newton meters, and it's pointing to the once again to the opposite direction, which means that we are going to be going from negative 60 to positive 20 value, like so. And finally we stay on this value until we reach the end where we once again have 20 newtons and we go back to 0, and it means that our structure is in equilibrium. We start from 0 and we end up to 0. and this one is positive. So that is our internal torque diagram. I like to highlight this cross section so it's easier to visualize what is the actual side here. So I visualize this like that. And now with this internal load, torque diagram, we can now easily calculate the stresses. So the formula for shear stress in case of twist was tau is torque divided by section modulus around axis x. And for cylindrical cross section, the Wx is pi times diameter power to 3 divided by 16, like so. These equations are available in your formula data sheets. So now we can calculate the shear stress for each of those cross sections separately. Tau 1, let's mark it here. We shall call this 1. This will be 2. This will be 3. So for cross section 1, tau 1, the internal torque is 10. It was Newton meters, so we must multiply 10 to the power 3 Newton millimeters divided by the Wx, the section modulus of the first cross section. It's pi times 8 power to 3 millimeter power to 3 divided by 16. And this one gives us a value of 99 megapascals. Then tau 2 is internal torque was 60, so it's 60 10 to power 3 Newton millimeters divided by pi times 15 to power to 3 millimeters power to 3 divided by 16. This will equal to minus, oh yeah, and this one is minus 91 megapascals. And finally, tau 3 equals to 20. The internal torque was 20 times 10 to power 3 Newton millimeters divided by pi times 6 to power 3 millimeter power to 3 divided by 16, which equals to 472 megapascals. So that's how you easily calculate the shear stress on shafts.